Hi, Year 13. This lesson we are going to continue with measuring the standard enthalpy change, but rather than use calorimetry, we are going to use bond enthalpies, sometimes called bond energies. Now, if you turn to page 34 in your notes, we are going to write in the definition of a bond enthalpy as the energy required to break 1 mole of covalent bonds averaged over many compounds. Now, if we take the example of methane, if we were to decompose methane into its constituent elements of carbon and hydrogen, we would require 1664 kilojoules of energy per mole to do that. There are 4 carbon-hydrogen bonds in methane, so it stands to reason then that if we divide the energy required by 4, this will give us a value of the energy needed to break 1 mole of these carbon-hydrogen bonds. Now, carbon-hydrogen bonds don't only occur in methane, they occur in lots of other compounds, and we're going to consider 3 more. So they occur in butane, in propane, and also in ethane. Now, we have just explained why the value to break a carbon-hydrogen bond is 416, and we used methane as an example when we were talking about that. Now, when you come to do the calculations, you will see that the value or the bond enthalpy of a carbon-hydrogen bond is actually 412 kilojoules per mole. There's a little bit of a difference there, and the reason comes in this second half of our definition. Now, if we were to only have methane, the value would be 416. But because carbon-hydrogen bonds occur in lots of different compounds, the experimental data is derived from all these different compounds, and we come up with this value of 412 when we average the energy required to break a carbon-hydrogen bond over lots of the different compounds that it occurs in. And all these bond enthalpies, 34, are always endothermic. We always require energy, and that makes sense to break a bond. Now, you won't need to learn any of these bond enthalpies. You will always be given this information in the question. Now, before we go too much further, we're going to consider what we already know about these energy diagrams, and we're going to tack a little bit of our knowledge on. Now, the first thing that you always need to do with an energy level diagram is to label the axes. And along the x-axis, we can have reaction or reaction progress. Now, let's consider the exothermic reaction first. We have got our reactants at this level of energy and our products at this level of energy. Now, let's apply what we've just talked about to these energy level diagrams. Now, the first thing that happens in any chemical reaction is that the bonds have to be broken. So the bonds in the reactants will be broken. They will free up the atoms in the reactants to move about and form products. Then when these atoms move about and arrange themselves into the products, bonds have got to be made. Now, it's really important that we remember that bond breaking is endothermic, it requires energy. Bond making is exothermic, it gives out energy, and overall we can see therefore then that the products have less energy than the reaction did. It's an exothermic reaction and delta H is negative. Let's go then and consider the endothermic reaction. Now, if we apply our knowledge in the same way, in the reactants all the bonds need to be broken. This is an endothermic process, it takes in energy. All the bonds then in the products have got to be formed, which is an exothermic process. So overall, the energy taken in is greater than the energy given out when these bonds are formed. So therefore, we have got an endothermic reaction and our delta H is positive. Now, we are going to use this knowledge about bonds broken and bonds formed and calculate the standard enthalpy change. Now we've got an equation there just below your energy level diagrams on page 35, and we're going to use this equation for this lesson. So the delta H, the standard enthalpy change, will be the sum of the bonds broken, take away the sum of the bonds made. Now it's important to realise that this is an approximate value for any reaction, and it harps back to our definition where we said that the bond enthalpy values were obtained by averaging over many compounds. So we're going to write into page 35. This is an approximate value because a bond energy is the mean value for a particular type of bond in several different compounds, and not necessarily the compounds that we're considering in the reaction. And that's an important point that comes up quite often in exam questions. Now, if you turn to page 37, we're going to consider an example. Now, we're asking example 1 to use the bond energies to estimate the delta H. Now, we're going to try to work out the delta H for the combustion of a molecule of methane. And this delta H is really then the delta HC that we talked about in previous lessons, because we are burning 1 mole of this methane completely in oxygen. Now it's a good idea to draw out the structures to avoid forgetting about any of the bonds that are being formed or broken. Now the first structure that we have got is methane. So if we draw ourselves out 1 molecule of methane, we have got carbon surrounded by 4 hydrogens. Okay, then we have got 2 molecules of this oxygen, and it's important to realise that the bond in oxygen is a double oxygen-oxygen bond. Going on to form then a molecule of carbon dioxide, and remember carbon dioxide has got carbon-oxygen double bonds, and 2 molecules of this bent water. And if you think back to your shape studies, it will help you out as to whether there are double or single bonds, or it is something that you will become familiar with the more of these questions that you do. Now we need to refer back to page 34 to find these actual bond enthalpy values. Now look carefully first of all at the reactants. We can clearly see that we are breaking 4 carbon-hydrogen bonds and 2 oxygen-oxygen bonds. If we pop in the values then, that will be 4 times 412 plus 2 times 496. Now the bonds that are being made then will be 2 carbon-oxygen double bonds plus a total of 4 oxygen-hydrogen bonds. And if we pop in the values, we'll go to our table and we'll find the the carbon-oxygen double bond, and we'll find that that has a value of 743. And then if we find our oxygen-hydrogen bonds, and there are 4 of them, 4 times 463. Now if we plug that carefully into our calculator then, and we do the final calculation, we find then that the standard enthalpy change for this reaction is minus 698. It's an exothermic reaction, and we would expect a combustion reaction to be an exothermic reaction. Now you can see there that it's dead easy to miss a bond, and in order to avoid that, I highly recommend that you draw out the structures of all the reactants and all the products. Now we're going of examples. So turn on to page 36, and we are going to consider question 2a. Now it does say there that we will use the values on page 62 but our values are actually on page 34. That's just a typo. Now, you're told for each of these to calculate the delta H, but you've got to balance the equations. Now, what we have got here is the delta HF for a molecule of ethene. We're forming 1 mole of ethene. Now, we need to balance it first. So in order to do that, we'll need a 2 in front of the carbon and a 2 in front of the hydrogen. Now, carbon is just an element. It's not joined to anything else, so I don't need to have any bond enthalpies there. But in hydrogen, I will have a hydrogen-hydrogen covalent bond, and we will have 2 of them, going on to form then this molecule of ethene. So ethene is an alkene. We've got a carbon-carbon double bond and 4 carbon-hydrogen bonds. Now, we'll use the values that on page 34. We've got to make sure that we total up the values for all the bonds broken and all the bonds formed. Now, for the broken, I'm going to have 2 hydrogen-hydrogen bonds. And I'm going to take from that then 1 carbon-carbon double bond and 4 carbon-hydrogen single bonds. And I'm going to pop in the values then. So 2 times 436, take away then 610 for our carbon-carbon double bond, plus 4 times 412. Pop that all really carefully into your calculator. Will be 872, take away 2,258, and we come out then with a value of minus 1,386 kilojoules per mole. Now, folks, I'd like you to pause the video, turn on in your notes then to number 3A, give 3A a go, and I'm just going to work through 3A as well, but you can see if you... Now, in number 3, all the values are given, so there's no need to look back, and we're asked to calculate the enthalpy change for the hydration of ethene. Now, I'm going to draw out all my structures to avoid missing any bonds. So we have got ethene, reacting with water to form a molecule of ethanol. And you can see the questions get a little bit more tricky. The molecules are bigger and consequently there are more bonds and it's easier to forget about a bond. Now I'm going to list all the bonds that are broken. So we've got a carbon-carbon double bond, 4 carbon-hydrogen bonds, and 2 oxygen-hydrogen bonds. And I'm going to pop in the values for these. So we will have our carbon-carbon, 612, 4 times our 412, and 2 times our 464. Now that gives a total value then for the bonds broken of 3,192. Now I'm going to go and do the same then for the bonds formed. We've got a carbon-carbon bond. We have 5 carbon-hydrogen bonds, 1 carbon-oxygen bond, and 1 oxygen-hydrogen bond. And I'm going to pop in the values. 347 kilojoules for the carbon-carbon, 5 times 400, and I see up above actually it's 413. I'll change that, and sometimes the questions vary a wee bit. We have got a carbon-oxygen bond, which is 358. and an oxygen hydrogen, which is 464. And I'm going to total up then the total for my bonds formed, and that is 3,234. Now when I go to work out delta H then, remember our delta H is always bonds broken, take away bonds formed, and the delta H works out at minus 42 kilojoules per mole.